Greetings and welcome to BSG webinars, everyone. My name is Jake Keeler, VP of Marketing at BSG, coming to you from my home office in Eagan, Minnesota. Thanks for joining us today. This is our second episode, so we're off and flying. Future episodes are posted on our website, as well as a link to video recordings of our past episodes, which is one so far. The page can be found by going to bsgcraftbrewing.com and clicking on webinars tile, or going directly to bsgcraftbrewing/webinars. We're aiming to have new webinars every Thursday at 1 p.m. Central Standard Time. Next week, we have Hop Creep, Review, Research, and Regulation with Chad Kennedy, our hop specialist at BSG Hops. And the following week, we have Long-Term Ingredient Storage Tips with Brandon Pierce, Quality Assurance and Compliance Manager at BSG. Throughout this webinar, please ask questions through the Q&A function, which should be found at the center of your toolbar. If we have time, I'll pass along some of those questions to our guest. And if you have follow-up questions, you can also send those and email them to webinars@bsgcraft.com. Again, that's webinars@bsgcraft.com. Today's speaker, Kevin Lane, Technical Sales Support Manager for the Americas from Fermentis, is going to be talking to us about his talk, which is entitled Technical Characteristics of SafSour LP652 and SafBrew LA-01, the newest products from Fermentis. And with that, I'll hand it over to Kevin.
Thanks, Jake. I appreciate the welcome, and I wanted to also thank BSG for holding this webinar and for inviting me to come on and talk about the two newest products from Fermentis. I have quite a bit of information to cover today, so we'll try to move through this quickly, hoping to still leave time at the end for a few questions at least. But as Jake said, we can answer follow-up questions through the email. So with that, I will... Oops. Sorry about that. So here, today we'll be talking about the technical characteristics of SafBrew LA-01, a yeast, and SafSour LP652, which is Fermentis' first bacteria for brewing. Again, my name is Kevin Lane, and I'm the Technical Sales Support Manager for the Americas for Fermentis. So we're going to start with the newest yeast from Fermentis, SafBrew LA-01. This strain was selected targeting non-alcoholic beer, NA beer, which is the NAB here. So it's NAB with SafBrew LA-01 targeting 0.5% alcohol or less. In this presentation, I'll cover quite a bit of introduction material at the beginning, just giving you as listeners an understanding of Fermentis and our production and quality of active dry yeast. We'll take a look at comparisons between potential microorganisms, and then get into the specifics of SafBrew LA-01 with the effects of the gravity on the fermentation, the effects of the temperature on the fermentation, and then at the end, more so a safety and quality control from your side as producers, looking at cross-contamination. So we'll begin with active dry yeast, the production and quality. So this is an image of the main yeast production plant for Fermentis. This is in Ghent, Belgium. It's quite a large facility, producing a lot of beer yeast, along with wine yeast, distilling yeast, cider, and even some baking yeast at this facility. When taking a look at the active dry yeast production process, you can see that all of our productions start with yeast that's in a cryo freezer, -80°C. That is then transferred to pure culture tubes, and then the multiplication begins. So the first couple of steps of multiplication are done in a laboratory in completely sterile environments, really just growing that single yeast strain. From the lab phase, which is where you can see the glass Carlsberg flask, which only has a few 100 grams of yeast in it, we move into pre-fermentation and then into the batch-fed fermentation or propagation system, in which we add the seed, which is the yeast starter from the previous steps. And to that, we can dose in sugar, oxygen, nutrients, vitamins, trace elements, minerals for the yeast to grow healthy. In this process, we're able to control those inputs and to really create the perfect environment for any yeast strain that we're trying to grow. Each yeast strain is going to have slightly different demand for different nutrients. So we do tailor each production, each yeast strain production to that strain specifically in both the growth, which is the top half of the slide, as well as the drying process. So just to give you an image of this propagation, we have this tank. If I remember correctly, it's about 5 or 6 floors tall. It's a huge tank, just for biomass production. Beyond the biomass production, we move through centrifugal separation, sometimes into cream storage at 4C. And then for all of the Fermentis product, we go through all the way to the right through vacuum filtration, through an extruder, and then to the drying plant. So just to give you an idea of what a vacuum filter looks like, it is this drum that's rotating, and the yeast is spread on the outside of the drum, where there's a vacuum coming inside, which pulls water through the drum. And then the yeast is then scraped off, as you can see in the image on the right. That then moves through to the drying process. Now, in these batch-fed propagation systems, like I said, we're able to control the inputs into the tank, and we can very specifically and accurately adjust how much of each or of any of the ingredients are going into the tank. And in that way, we're able to limit or to decrease some of the inputs to have all the yeast that are multiplying inside of that propagation to be roughly at the same stage, where they've split from each other after the replication has started. And they're 2 individual cells rather than a cell that's budding or in part of that segregation or division cycle. And that's important to maximize the viable cells moving forward. So we're purposely going through production, and then towards the end, when we reach a certain volume, we reach a certain biomass that we're targeting, we limit the inputs to slow down the cycle, to stop the cycle, so that we can have all the cells at the same point to move forward with the drying. In this, the yeast also has plenty of trehalose and ergosterols present, which then enable the yeast to start fermentation right away once it's rehydrated. So all of the work that we go into in the production process is to have the yeast at the right stage for us to dry it, so that when a brewer or distiller or winemaker, any end user goes to use the yeast, it's ready and it's highly viable. Whenever we bring a new strain into our system, it always first enters into LaSaf, into the R&D collection. And when we put a new strain into that collection, we always do genetic purity and properties testing on it to make a standard for that strain. From there, we do a multiplication where we also check the genetic purity and properties, and that goes into a second yeast collection, which is more targeting for the physical production. So we do have thousands of yeast strains in a bank, or in multiple banks actually. Some of them are industrialized, some of them are not. So the R&D collection has all of the strains that we have. The industrial collection just has the strains that we're moving forward with in terms of production. From that industrial collection, we again do multiplication to create what we call daughter line yeast tubes. These are again tested for genetics, purity, and properties of that strain. And those are then what are sent to the factories around the world. So when we schedule a production of a certain strain, we have one of these daughter line yeast tubes sent, and those are always checked for genetics and properties as well. In the production facility, the facility receives those daughter line yeast tubes from the global bank or from the lab, and then those enter into that laboratory phase that I showed a few slides ago. In the laboratory propagation, we are producing yeast, we're producing biomass to move into the full-scale propagation, the industrial phase. So after the laboratory propagation, we also do purity control. And then in the industrial phase, we're doing biomass production and then drying. And then it goes into storage at our facility for analysis, where we run purity, composition, aging, and properties testing before the product has a positive quality release and is then sent to Fermentis customers. So the reasoning behind those slides is to show you that we do check the yeast over and over and over to make sure that what we received at the beginning or what we had from the beginning is what's in the package moving forward, coming out to you as customers. In terms of the active dry yeast production, we have two slides here. One, this is for lager yeast. So when you see the Fermentis technical data sheet, or you see the quality specifications on any of the yeast, you see something more along the left side where we have the viable yeast at greater than 6 billion cells per gram. And then we have lactic acid bacteria, acetic acid bacteria, Pediococcus, total bacteria, and wild yeast with the levels stated as quality statements. When you take those numbers and elaborate for what is true when you pitch on average for our lager yeast 100 grams per hectoliter, you end up with a viable cell count of greater than 6 million cells per milliliter. When you take those bacteria counts or wild yeast counts on the left side and calculate that out based on the pitch rate, it means that in a pitch of 100 grams per hectoliter, there's less than 1 colony forming unit of any of the bacteria per milliliter. It's an extremely pure product. It isn't 100% pure, we state that, but it is a very, very pure product. And here we can say that it's 99.999% pure. Or what we could say is there's less than 1 bacteria per 6 million viable yeast cells, which is pretty significant. Here's a similar slide, but specifically for ale yeast, which is what we'll be talking about in a minute with the SafBrew LA-01. Again, similar numbers, they're slightly different based on the cell size and the pitching rate on the right, but what you see is that based on a 50 gram per hectoliter pitch rate, you will end up with greater than 5 million cells per milliliter, and again, less than 1 CFU per milliliter of bacteria. Again, a 99.999% pure product. So now getting more specifically into SafBrew LA-01 for non-alcoholic beer or NA beer. When we started to look into new yeast strains to brew low or non-alcohol beers, we had some general ideas in mind. The first being that we for sure needed this yeast strain to be maltose negative, so that it wasn't capable of fermenting maltose. We needed the presence of aromatic fractions that you would expect from a beer, and we wanted low phenol expression. And our idea behind it was that this strain should present some important differences compared to Saccharomyces cerevisiae in the way that this yeast assimilates sugars present in the wort. Given that a typical wort composition is going to have 10 to 15% monosaccharide in weight, weight to weight, which is what you see here with the glucose, 10 to 15%. With us wanting a maltose negative strain, we're counting on this strain only fermenting the glucose or fructose, the monosaccharides, the simple sugars, and not touching maltose or maltotriose or the dextrins. So we did some trials in flasks, comparing a lot of the commercially available, the more typical used strains for NA beer or low alcohol beer. So we have SafBrew LA-01, sorry, there's a mistake there. SafBrew LA-01, which is a Saccharomyces cerevisiae chevalieri variety. And then we compared that with Pichia, with Ludwigi, with Torulaspora, with Roxy, in just a very standardized wort for fermentation, for flavor, and for different analysis. The wort was 100% Pils malt, standard mash diagram targeting 12 Plato and 25 bitterness units with just mosaic hop pellets at the beginning of the boil. Mashed at 65 degrees C for 50 minutes and then 73 degrees C for 10 minutes. The temperature of fermentation, we ran two side by side with SafBrew LA-01, one at 22 C and one at 10 C, which 22 C is roughly 74 degrees, 73, 74 degrees, and 10 degrees C is roughly 50, let me get this right, roughly 50 degrees. We produced a 12 plate of wort, but then we did dilutions of that to 8 degrees Plato and targeting 16 BU to get the 0.5 ABV. So in the analysis of these strains, you can see the alcohol produced by each of the different yeast strains. And then some notes at the bottom where the Torulaspora and Ludwigi are maltose positive, but very slow, which runs a risk of potential over attenuation if it's not given enough time. The Pichia and Roxy do not consume all the simple sugars, so it may produce a sweeter beer in the end. And then the strain that we selected, the Chevalieri, stops after the consumption of simple sugars with less risk of over attenuation. These were the 22 degrees C fermentations. And then we took the resulting beer from those fermentations and had to go through a tasting panel. I think it was a rather small tasting panel, but just blindly tasted to see what the tasters came out with. And what we found was the Torulaspora produced a natural malty and worty beer, neutral malty and worty beer. Ludwigi produced a well-balanced and fruity beer with a slight touch of DMS. The Roxy produced a beer with a lot of off flavors. The Pichia, fruity beer with a really high level of isoamylactide and poor drinkability. And then the strain that we selected to move forward with, the SafBrew LA-01, produced good beers, maybe a slight phenolic character, but what was communicated was that it isn't going to be like a really phenolic beer, but rather the slight phenolic that's produced by this strain gives a little bit more complexity to the low alcohol beer. So we decided to select SafBrew LA-01 and move forward with that. When taking a look at the genetics of this strain, the strain that we selected, you can see on this phylogenetic tree of yeast where the SafBrew LA-01 fits. It's actually in the sake clave, which there's also another one of our products there, HA18, which is a few branches away. But interesting that this strain falls into the sake yeast clave. So now we're going to take a look at the effect of gravity and temperature on this strain specifically. So again, we set up experimental protocols. Flask tests were performed with the following conditions. It was SafBrew LA-01, again, remembers the Chevalier strain, pitched at 50 grams per hectoliter, and then Weyermann Wort at 15 Plato, and fermentation temperature of 20 degrees C. What you can see here is really the fermentation kinetics. You can see the growth, the acceleration, and then the end of fermentation. Really what we found with any of the different gravities is that these fermentations are lasting roughly 75 hours, give or take. And you can see here that if you're at 15 Plato, you will achieve roughly 1.2% alcohol by volume. At 10 Plato, you'll be at about 0.75. And then somewhere between 6 and 8 Plato is really the sweet spot where you can label it as an NA beer, that being 0.5% alcohol or less. When taking a look at these fermentations in terms of apparent degree of fermentation or attenuation level, you can see that generally they're between 13 and 14% ADF, which is what we're expecting. Again, remember, one of the introductory slides was showing the sugar composition of a typical wort, and that said somewhere between 10 and 15% of the sugar would be monosaccharide glucose. So we're seeing that this Chevalier yeast is fermenting just the simple sugar and stopping there. Here, a different analysis where we're actually seeing the individual sugars. So you can see fructose in blue, glucose in orange, DP2 or maltose, potentially sucrose in gray, and then in yellow, the DP3 or the maltotriose. What you can see is that the fructose and the glucose are completely consumed, maybe a very, very, very slight residual glucose for the 15 Plato. But overall, the fructose and glucose are fully consumed, and the DP2, DP3 are not touched by this strain. Again, an analysis at the end of the fermentation, taking a look at the amount of ethanol produced. And you can see that obviously when you increase the starting gravity, you're seeing an increase in the alcohol of the ABV produced by this yeast strain. But we were kind of curious if there was a direct correlation between the ABV and the original gravity. So we ran a correlation test. And in fact, it is a linear regression between the alcohol by volume and the OG. So we can say with a high amount of certainty that the alcohol produced is based on the amount of monosaccharides available in the wort. Again, with this linear regression, we can see that somewhere between 7 and 8 Plato is where we're going to reach that 0.5% ABV. Another aspect that we wanted from this yeast strain was that it was going to produce the aromatic compounds that you would expect coming from a beer. So we did the volatile compound analysis after the fermentation, and you can see that the acetaldehyde was above threshold, isoamyl alcohol was below threshold, the isobutanol was below threshold, and the diacetyl was below threshold. Even if some of these volatile compounds are below threshold, their presence in the mixture will give you more or less a beer flavor or beer aroma. So even if these are the isoamyl alcohol, the isobutanol are below threshold, they're still giving some complexity to these low alcohol beers, which will therefore taste more like a beer. Again, we ran a test where we fermented with SafBrew LA-01 at 10 degrees and at 22 degrees C. And here you can see that there was a difference in the resulting beer, that the beer fermented at 10 degrees C was not as complete. which means that there were more residual fermentable sugars in that beer, which is a little bit dangerous, a little risky, given that nearly every yeast, if not all yeast, will ferment that sugar because it's monosaccharide. So we recommend definitely to be above 10 degrees C, but there was no significant difference in the aromatic production between these two beers. So the first conclusions we could say are that LA-01 produces well-balanced beers, maybe a slight phenolic present, without any defects, but preferably fermented above 10 degrees C. The resulting beer, and this is an important point that I want to emphasize with all of you, the resulting beer is going to contain a lot of residual sugar. That residual sugar will be fermentable by all of the other yeast strains that you're using in your brewery. So with an NA beer or low alcohol beer, you have to be very cautious and be safe with the beer after the fermentation is complete with SafBrew LA-01 because of that potential for a second fermentation from any of the other yeast strains that you're using. So from the Fermentis standpoint, we say pasteurization is mandatory to stabilize this beer, and that's pasteurization in the package, not flash pasteurizing before going to the filler. And that's for your safety, that's for your employee safety, that's for your consumer safety, that we strongly recommend. We say it's mandatory that you pasteurize this product. Taking a look at the pasteurization, we wanted to focus on cross-contamination and how pasteurization affects that. So we just give you a quick, brief definition of pasteurization. It's an equivalent of 1 minute at 60 degrees C. This can be done at different temperatures, of course. So the higher the temperature you go, the shorter the amount of time you need to achieve one pasteurization unit. And there's really two types of pasteurizers that we recommend. And that's tunnel pasteurizing, where the beer is moving through a tunnel and the water temperature is changing at every step as the beer moves through the tunnel. Or there's flash pasteurizing, which we don't recommend for this type of beer because there is a step in between the tunnel between the flash pasteurizer and the filler. The other type of pasteurization that you could use would be a batch pasteurizer, where you have one tank where the water is changing temperature and recirculating, but that's a different conversation. In terms of the recommendations for pasteurization units, or PU, the EBC recommendation for low alcohol beer, which is somewhere, I think, less than 2 or 3, is 40 to 60 pasteurization units for non-alcohol beer, which is what we're talking about. Although you could make a low alcohol beer with this yeast strain, it would just have to be a higher starting gravity. For non-alcohol beer, the EBC recommends 80 to 120 pasteurization units. Fermentis' recommendation on the technical data sheet is 100 pasteurization units after packaging. But we'll take a closer look at that with an additional study that we ran. So we did a trial where we did a fermentation with SafBrew LA-01 at 25 degrees C. We centrifuged it, and then we purposely cross-contaminated with SafAle T58. And the reason that we chose that strain is it's one of the most robust strains in our product portfolio. So it has a strong resistance to pasteurization compared to, for example, lager yeast, which are more susceptible. So we cross-contaminated with T58 at 0 CFU per ml, 10 to the 3, 10 to the 4, and 10 to the 5, pasteurized at 63 degrees C, and then checked by plating on YPD media if there was any growth after 25, 50, 75, and 100 PU. Here are the results of this test. So what we see is the green is 25 pasteurization units. The red although you don't see any bars, is 50 pasteurization units. And then what you see in terms of the bars is the cell count of T58. In theory, it could have been LA-01, but our assumption is that it's T58. Either way, we're seeing yeast cell growth or yeast cells still alive when it's only 25 pasteurization units. However, once you reach 50, you do not see any growth. So what we can say is that a minimum of 50 PU is mandatory for this type of beer. So to conclude on the SafBrew LA-01, we recommend a pitching rate of 50 grams per hectoliter, fermentation temperature of 15 to 25 degrees C. You should expect an apparent degree of fermentation somewhere around 15%. In a traditional brewing diagram, the alcohol produced should be roughly 0.5% ABV for 7 to 8 Plato, a pH of around 4.5. With the SafBrew LA-01, no off flavors. Pasteurization should be 50 to 100 pasteurization units. And then we strongly recommend not repitching and no re-fermentation. So not repitching because this product, a non-alcoholic beer, is so sensitive to any potential contamination in the brewery that if you collect the yeast and try to repitch it, try to reuse it for a different batch, there's a much higher possibility with this that you'll have over attenuation, you'll have more alcohol produced than you're hoping or expecting. And then the second point, the no re-fermentation, there's a couple of reasons. Again, you could have contamination in that if you're using a different yeast strain, or, and what I think is the bigger part of that, is when you have re-fermentation, you have more alcohol produced. So you wouldn't be at the 0.5 ABV anymore. So that is the conclusion of SafBrew LA-01, the newest yeast strain from Fermentis. Looking at the time, I'm going to quickly transition into the SafSour LP652 because I'm trying to keep this to a reasonable amount of time. SafSour LP652 is a new category for us, SafSour. It's our first bacteria for the brewing industry. It is a lactic acid bacteria for wort acidification. So SafSour LP652 was selected by Fermentis. It's ideal for kettle sour beers. SafSour LP652 releases more or less a tropical citrusy and fruity note with a freshness sensation. And from our analysis, we can consider it homofermentative lactic acid bacteria, LAB, producing mainly lactic acid in this bacterial fermentation. Additionally, it is easy to use, ETU. If you're not familiar with that topic, I can explain it to you at a different time. But essentially what it means is that there's no difference in terms of viability or vitality in changing the way that you're using the yeast and, or in this case, bacteria, or potentially even some of our other products. For this presentation, we'll take a look at the beer and sour beer process, how that fits in. The fermentative potential of SafSour LP652, targeting 4 different arenas, if you will, the add rate, the pitch rate, the wort density, the temperature, and the agitation on that fermentation, to see what the best conditions are or what to avoid. And then at the end, we'll take a look at the organoleptic profile in the wort. So here, if you're a brewer, I hope you're familiar with this process. This is your brew day, basically. For the left portion of it, and then into fermentation, maturation, and then to some sort of packaged product at the end. What we're going to take a look at specifically with this is the portion that drops down in between lautering and boiling, which will be a kettle sour. where you're doing a standard mash, standard lauter, bringing that to a boil, and then cooling it back down and starting a lactic fermentation with the bacteria. And then after you're satisfied with the acidification, then returning to the process, boiling, hopping, and moving forward. So we'll start by taking a look at the fermentative potential of SafSour LP652 for non-hopped wort acidification. That's a key point there, non-hopped. You do not want to hop this wort before you do the acidification for the bacterial fermentation. Excuse me. So we'll take a look specifically at this bacteria in terms of if you change the pitching rate from 10 gram per hectoliter up to 100 gram per hectoliter, how does that affect the fermentation, the souring? We'll take a look at 3 different Plato densities, 8, 12, and 16. And then we'll take a look at the temperature's influence on the pH drop or acidification. And then we'll take a look at the agitation, whether it's important to agitate or not. I can tell you that from this moving forward, the agitation does not affect the souring, and the wort density, although there's a change, it shouldn't really affect the acidification. So let's take a look at the pitching rate influence on acidification and lactic acid production. Here you can see in the solid line that the solid line is 10 gram per hectoliter. The dashed line is 100 gram per hectoliter. It should make sense that you have a faster pH drop with the 100 gram per hectoliter. However, what you're seeing with the final pH after a 48-hour period of time, the pH isn't that significantly different between these two pitch rates, one being 10 times the amount. So really, we can say that by increasing the pitching rate, the fermentation time drops and the final pH is slightly lower. But with either pitching rate, the acidification is complete within 24 to 36 hours. Here is for those two add rates as well. You can see the 10 gram per hectoliter on the left and the 100 gram per hectoliter on the right, the gray bar being the 24-hour mark and the blue bar being 48 hours. And this is the amount of lactic acid in terms of gram per liter produced by the bacteria in those periods of time. So a rise in the pitching rate increases the lactic acid production in terms of speed and the amount. How does the wort density impact the acidification and lactic acid production? Here, it's a little interesting to see that really we're not seeing a difference in the pH between the 8 Plato, 12, and 16, although the 16 Plato pH is slightly higher throughout the entire process. And you can see that the 8 Plato is a little bit faster at the beginning, but still achieving basically the same pH at the end of the 48-hour mark. So we can say that the low wort density promotes acidification in terms of pH, and that's more so, I think, the buffering capability of the wort versus the amount of acid produced. Here, again, you can see 8 Plato, 12, and 16 Plato, gray being 24 hours, the blue being 48 hours, and the amount of lactic acid in grams per liter produced. Really what we're seeing here is that at 8 Plato, you're having technically, I would say, a slightly more efficient souring, just because you're not seeing a doubling of that for the 16 Plato. But you are seeing an increase in lactic acid production at 16 Plato. So low wort density reduces slightly the lactic acid production, albeit a little bit more efficient in terms of the sugar. How does the temperature influence the acidification and lactic acid production? This I found really interesting when I saw it the first time, because I always was thinking that bacteria favored high temperatures in mid 40s up to 50 degrees C. But with this particular Lactobacillus plantarum, which is why it's called LP652, so Lactobacillus plantarum, if I didn't mention that already, you can see that it actually favors the lower temperature, somewhere in the 30s up to 40 degrees C. If you were to use this bacteria at 45 or 50 degrees C, you can see that you won't have an efficient souring of the wort. So that's one of the key takeaways is with this bacteria specifically, we want to be in the 30s up to 40 degrees C. Here is the amount of lactic acid produced, again, at 24 and 48 hours. Across the bottom, you can see 37 degrees, 40, 45, and 50 degrees C. And then you can see the amount of lactic acid produced in grams per liter for each of those temperatures. And you should clearly be able to see that at 37 C. With all else the same, you have more lactic acid production. So temperatures higher than 40 C impact the lactic acid production drastically, and you can see that with the 45 and 50 degrees C, that there is very little lactic acid produced. How does agitation influence the acidification? Again, this is side by side, same wort, fermentation, a static fermentation with no agitation or 100 RPM in the dashed line. And as you follow along, there really isn't a significant difference in the pH drop, and both actually reach the same terminal pH at 48 hours. So we can say that there's no significant influence of agitation on acidification. So conclusions on this: how to fine tune acidification, increase the pitch rate to increase the speed and amount of acid produced, and decrease the wort density for efficiency. And in any case, the temperature for the lactic fermentation should be between 30 and 40 degrees C. Now, what I think is especially interesting with this product, SafSour LP652, is the organoleptic profile of it that it imparts on the wort. And this is a study that we conducted within Fermentis in our internal taste panel, which is, I think, today close to 50 or 60 trained tasters. Not necessarily all devoted to the beer industry, but from all different walks of life. What we did for this experiment was we did a Pilsner non-hopped wort at 12 Plato. We did one lactic fermentation with 10 grams per hectoliter and one with 100 grams per hectoliter. And we also kept one of the worts non-fermented. So we have a comparison at the end. The fermentation was carried out for 48 hours at 30 degrees C. And then, like I said, this went through our internal taste panel with at least 22 members tasting. And for this soured wort, this acidified wort, we asked specifically for the descriptors of volatile acidity, dairy, fruity, malty, cereal, acidity, sweetener, bitterness, honey, and sulfury. So when we take a look at the wort that was non-fermented, we have this image. So not very much dairy, not very much volatile acidity, no bitterness, low acidity, high sweetness, high honey, high cereal, high malty, and low sulfury, low fruity. So that's the wort that's unfermented by the bacteria. And then we introduce the two different trials with the souring fermentation, the acidification. And what you can see is, should be somewhat easy to understand. You have a decreased sweetness, a decreased honey, decreased cereal, decreased maltiness. And then you really see the profile of the bacteria here, a little bit of sulfury note, which is more typical with a kettle sour. Nothing too strong, but present. Fruitiness for sure, dairy, volatile acidity. Bitterness is still nothing because there's no hops, and a strong acidity. with each of these, you can see the significance of the difference, the change by the number of asterisks next to the flavor. So where you see acidity, sweetness, honey, malty, those had the most dramatic change. And then the second most dramatic were cereal, sulfury, fruity. And last is the change in the dairy character. With it, with our internal taste panel, they described it as a tropical, fruity, citrusy, lemony type flavor coming from this bacteria, which is somewhat expected, but really a very nice sour wort. So getting to the conclusions for this strain, this product, SafSour LP652, we say for standard wort acidification, it should be a pitching rate of 10 grams per hectoliter. Of course, you can increase that if you want to. We saw that if you do increase it, you do have slightly faster souring acidification. The lactic acid fermentation time is roughly 24 to 36 hours, maybe out to 48 hours, depending on what you're doing or how you're running your brewery. The temperature range is from 30 up to 40 degrees C, targeting a pH at the end of this of 3.2 to 3.6. The organoleptic profile of this non-hopped wort, we have an increase in fruitiness, acidity, and dairy perception, and a decrease in the malty and sweetness perception from our taste panel. And we say it's a highly reliable bacteria to create a balanced sour beer in terms of kettle souring. So with that, I am done with my presentation to you today. I think we will go back to Jake.
Yeah. Thank you, Kevin. That was awesome. Ton of information in there. So just to remind everybody, we are recording this session and we'll be posting that to YouTube on our BSG Craft Brewing channel. That link will be available again on the BSG/webinars page. So we did have a couple questions come in through the talk. So we have a bit of time here to answer those. And it's actually kind of a two-part question, Kevin. So I'll start with the first part. This is in regards to LA-01 specifically. And the question is, would dry or wet yeast make a difference in the flavor profile of beer?
So the form of the yeast itself?
Correct. Yeah, I think that's what, yeah, exactly.
You know, I don't think that it should. Really, when we do our analysis for recommending pitch rate or temperature for a certain strain, we're targeting what that strain should taste like in a beer, whether it's, you know, an American type ale yeast strain or a Belgian type yeast strain.
Mm-hmm.
Really, there shouldn't be a change from liquid to dry format. I don't think that should change the profile of the yeast or how it imparts flavor into the beer in general.
Gotcha. And then the second question is kind of builds off of that. How might different malt types affect the fermentation profile of LA-01?
For sure, it's not something I talked about. You know, it's a challenge because what I often tell customers is yeast is going to do what the yeast is capable of. And I say that because whenever you start to change ingredients, you're changing the composition of what you're fermenting. Whether that's creating more fermentable sugars or less fermentable sugars, you know, that will affect the fermentation. So if for some reason, if you're getting more glucose from adding one malt versus a different, or if you're adding sugar to the fermentation, you know, table sugar or dextrose, glucose, you're affecting the composition of the malt itself in terms of the sugar profile. Mm-hmm. So the yeast will perform different because they're going to ferment what they can ferment. They're trying to survive. You know, the yeast isn't there trying to make a beer. That's
Mhm.
kind of the consequence of what it's doing, trying to survive, is it makes beer. So, it's something that we didn't really explore, changing the malt or changing those types of parameters. Uh, it's not something that I think it's something that we could investigate in the future for sure. We started to do that with all of our yeast strains, one at a time, changing certain fermentation characteristics to see how that affects the flavor profile of the fermentation. So at some point, I think we might revisit that. Also, internally, we're doing more applied research on how yeast are interacting with the ingredients. So we came out with some studies on the yeast and hop interaction. I know that there is some concept, and at this point, all I can say that it's a concept to do something similar with malt. So
Right.
I think it's an interesting avenue. Unfortunately, or however you look at it, this is a new product, so we're bringing to the market our understanding of it and how you can make a low alcohol or a non-alcoholic beer with that yeast.
Yeah. And I guess I'd add too that, I mean, and maybe you can talk to this, but as these new yeasts are out there and breweries start using them, I would imagine you'd welcome that feedback in terms of what brewers are seeing working with those different ingredients, and a feedback loop to you or through BSG.
No,
It's
for sure. I mean, I think you hit on a really important topic to me, and that's, our applied research internally is Fermentis research,
right,
but that's just research to help the brewer to figure out, how to use something or what the right parameters are.
right,
In terms of the actual usage, that's done by the brewers, not by
right,
us. So
right.
I think, I encourage the brewers to get back to BSG or even to come directly to Fermentis and share
Mhm.
their information with us, because in the end, we're trying to help the brewer make better decisions as to how to use something. And maybe we're not exploring everything. Um,
Absolutely.
and craft brewers, I love you guys, but you're crazy sometimes. So you might do things a little bit out of the box, which we might not do in a test.
Absolutely. I got a question now. I'll pivot to SafSour. Is a really straightforward question here. Does SafSour need to be handled any differently than a typical dry yeast?
Um, it's a great question. Uh, it is more temperature sensitive. So what we recommend is when the brewer receives the bacteria, to freeze it, to put it into a freezer if you can. Of course, refrigeration is also okay, but it's a different production process. It's actually freeze dried rather than the active dry yeast being dried the way that that's done. Um, in terms of usage, no. I mean, it's the same.
Mhm.
It's interesting because I've used other bacteria in the past in my former life as a brewer, and I remember the dried bacteria being more spherical in shape and
Hmm.
physical structure. This is more or less like a powder or flaked almost. It looks
Okay.
so. I think it's milled after the drying. But in terms of using it, it's easy to use. Again, I think if you don't know what that is, get in contact with Fermentis or with BSG. I think you guys know what that is by now.
Right.
But it's easy to use, so you can add it. You can rehydrate it if you want. You don't have to. There's a relatively large window of temperatures that you could add that to your fermentation.
Great. And then another question on SafSour. It says here, I know you emphasize the use of LP652 in non-hopped beer. Does any amount of hops completely inhibit LP652's activity?
It's a great question. From our internal research, from what I know, I think that it was something like between 5 and 10 ppm was the limit for that. We recommend unhopped, non-hopped, because then you can really have a consistent souring.
Mhm.
So rather than complicate it further by having some issues with sensitivity, if you just avoid hopping completely, you have unhopped, which is therefore better for the bacteria. So not to say that you can't. I don't know for certain that you can't hop at all, but we recommend not hopping so that it's a very consistent process, so that when you do it the first time versus the 25th time, it's the same process and you're not having a difference in time or a difference in acidity. Really, it's the idea is to have the same product in the same time.
Gotcha. And then this gets into a bit more specific about a beer style. Which Fermentis active dry yeast would you recommend for Berliner Weiss in combination with LP652?
That's a great question, and unfortunately, I don't have the answer for that today. For us, it's challenging because right now we don't yet have our physical Fermentis Academy.
Yep.
It's coming. We will have a physical facility for doing tests. So right now we're a little bit limited. I think we have done some research into fermenting with the Fermentis products as post souring. But I don't have that information. My guess would, and this is just a guess, my guess would be that WB06 would probably be one of the better options. But I think it brings up another question or another answer, and that's one that I'm familiar with saying is it's up to the end user. I mean, you're looking for what you want in that beer. And for me to make a recommendation for a certain style is just, that's my opinion. And I think that's the beauty of craft beer in general, or even brewing in general, is you can do really what you want to create the product that you want. It's
Right.
not that you have to use part A and part B together in this way to create beer X or something. You have that option to try different strains and find out what flavor profile you like. I can say that I have used the LP652 at home and at one commercial brewery, and it does play really nice with K97.
Okay.
It produces really a really nice flavor. And if you use it with B134, it produces a really strong citrusy kind of orange lemon. Like the two together is really interesting. But I've only done those two, so I don't know beyond that.
Right. But I guess it kind of goes back to the point, that especially when new products are introduced, it's like you guys obviously set up some guideposts, and there's the technical information, and people understand how it's going to work. But after that, breweries are going to do all kinds of different things with it. They're going to, whether it's the mash bill or the hops they use or the other yeast they use, the ingredients, and then the whole process itself. It makes me think, like, when people start using it, that's why that community is so important. That's why that feedback loop is so important, that people are sharing that information. So
right. And I mean, we get some of it too, just by knowing the customers and tasting the beers that they make.
Right.
One example was at Brow last year. We had a kettle soured beer with K97 with Galaxy hops, and there was, I think, passion fruit and mango addition to the fermentation.
Wow.
And it was beautiful. I mean, it was this great combination. Certainly not something that Fermentis tested. It was just, from the Fermentis side, I would say we approach it more scientifically and leave that artistry or the creativity to the brewer, because they have all of those options to play and to hop in different ways and different malts. What we're trying to deliver is more the technical background so that the brewer can make those choices and say, oh, I wonder what would happen if this. Yeah. And for them to be creative and do that with our products, knowing, okay, with LP652, I need to keep that acidification between 30 and 40 C. Okay, that's great for an end user. What they do beyond that, that's the creativity of brewing.
Yeah. That's awesome. Well, I think our time is almost up, and that sounds like a good note to end it on. Kevin, I want to thank you again for your time, and Fermentis as well for bringing all this information to us. I think this is pretty amazing. If we didn't get to any of the questions, I think there's maybe one outstanding. We'll try to answer those offline. we'll pass these questions along to Kevin and get those answers. And then if you have questions, folks, that you think of later on, you can send those again to webinars@bsgcraft.com. We'll take those questions, pass them to Kevin, and get those answers and send them back. Kevin, once again, thank you so much. Thanks everybody for tuning in. Remember, you can register for the next webinars on our page at craftbrewing/webinars. And from everybody at BSG and Fermentis, take care and we'll see you soon. Bye.
Thank you. Cheers.